Good afternoon, all. I hope I'm audible to everyone. Good afternoon, good evening, wherever you are joining from. Welcome to another talk from Kerala Theoretical Physics Initiative, and welcome to this group as well. So, Kerala Theoretical Physics Initiative is a collective of faculties, postdoctoral fellows, and PhD students across the globe who are originally from Kerala. KTPI aims to create a home for research and education in physical sciences by focusing on theoretical approaches. Our goal is to establish a research-friendly atmosphere at an undergraduate and postgraduate levels in Kerala. We are planning to achieve this goal by fostering strong collaboration among ourselves and within the colleges in Kerala. So as part of this KTPI program, we have two main events going on. One is the ART program, which stands for Active Research Training, which helps postgraduate students and occasionally undergraduate students to work on active research areas along with other people who are actually researchers, including postdoctoral fellows and faculties from various institutions. And another program is the lecture series where we invite people who are well established in research, especially in theory, but not exclusively to theory. We also encourage other people to come across and share their wisdom with us. And today we have another talk, and I invite Karthik to introduce our speaker.
Thanks, Manoj. Hello, everyone, and welcome to another talk of KTPI. Today, I'm very glad to introduce our speaker, Dr. Sreenath Manikandan. Sreenath is an expert in quantum information, quantum sensing, and several things related to quantum theory. He did his master's from ISET Trivandrum, where incidentally I also did my master's from. I very vividly remember the very, the very bright two brothers, Sreenath and his brother Srikanth. They were almost always topping the courses, and if I remember correctly, they also got the gold medal from the institute. And Srinath from ISER, he went on to University of Rochester for his PhD research, and then he held a postdoctoral position at Nordita, where he was Wallenberg Institute Fellow, I think, and now he's a researcher in the theoretical group of Frank Wilczek, who is a Nobel laureate in physics. And today he's going to talk on a very interesting topic of detection of the quantized gravitational field using some not so far futuristic experimental setups. So Srinath, please.
Thank you both Manoj and Karthik, and thank you for the introduction. And I also want to thank you for this program that you have continuing. I have listened to some of the talks previously, and they were really nice. And it is indeed a great platform for students in their early career stages. So I'll share my slides. Yeah, let me also get the okay, so this today's talk, I am going to discuss the problem of detecting single gravitons using quantum sensing, and it is a work completed with the group of Igor Pikovski, who is both at Stockholm University and Stevens Institute of Technology, New Jersey, and PhD students Thomas Beitel, who is at Stevens Institute of Technology, and also Germain Tobar, who is a PhD student at Stockholm University. So the problem is about detecting individual graviton exchange events between matter and gravitational waves. But I would like to start this talk with a brief recap of the early 1900s of quantum mechanics, where quantum mechanics as a theory was rapidly developing. And there were two key experiments that led to the most important insight that photons or light can be thought of as quantized packets of energy in exchange when energy is exchanged between light and matter. I would also want to mention that if you have any questions in between, please stop me in between, or you can also ask in the end. But if you have some questions in between, please do stop me and ask the question. So the first experiment or the major step was Planck's explanation for the blackbody radiation spectrum. And the interesting observation was that black bodies, when the blackbody radiation spectrum is the spectrum of radiation or measured intensity as a function of wavelength or frequency and temperature. So there was a very good classical reasoning which used equipartition theorem and classical statistical mechanics at the time, and Maxwell's electromagnetism, classical electromagnetism at the time, which explained the behavior at very high wavelengths or low frequencies and high temperatures. And this is the formula, the fit to the blackbody radiation spectrum in this regime was provided by Rayleigh and Jeans. So it's the Rayleigh-Jeans formula, but it tend to deviate very much at the low wavelength or high frequency regime. There was another competing explanation, which was Willem Wien's formula, which actually was working very well in the low wavelength regime or high frequency regime. And Planck was the person who basically came up with the formula for the blackbody radiation spectrum that worked across all frequency ranges and all temperatures. And the genius of Planck was not just in coming up with a fit for this blackbody radiation spectrum across all frequencies, but then he also tried to interpret what does it mean. And the idea that he had was that one could think about a black body as a collection of oscillators, which the radiation as these oscillators exchanging energy, but proportional, the oscillators only populate the cavity, which he modeled the black body as a cavity with the dipole oscillators and on the walls. And they only produced energy proportional to the frequency of these oscillators and in discrete units. And this proportionality constant is what we now call the Planck's constant. Now, Einstein was actually quite interested in the high frequency result to explain blackbody radiation spectrum. The Willem Wien's formula, which worked very well at high frequencies. And he was also working on statistical mechanics quite a bit at the time. So he considered, for example, he considered a box of light at high frequencies, where looking at computing the entropy of light, a high frequency light constrained to a box or a volume. He was able to compute that the result for entropy behaved as if it corresponds to number of particles having a certain distribution. And this statistical inference further led to Einstein to think that light behaves like bundles of energy. Not only that, he also used this as an insight to predict what happens when light interacts with matter. For instance, in the photoelectric effect. The key observation in the photoelectric effect is that when you shine light bulb on metal surfaces, let's say, then electrons are emitted. But then there is a threshold frequency below which you don't see, even if you increase the intensity of the light, you don't see photoelectrons emitted. And then the stopping potential, so one could try to stop the electrons that are emitted from metal surfaces by applying a stopping voltage. And this stopping voltage was, once you increase once you are above the threshold frequency, the stopping potential was independent of the intensity. Again, it was what one would see is that more number of photoelectrons are emitted once you increase the light's frequency. So the light's intensity once you have the threshold frequency, but the stopping potential energy was the same. So these two, the genius of Einstein here is essentially that he combined these ideas to say that light, not only in existence, but also in interactions with matter, it behaved as if it consists of particles. And this is known as the light quantum. He postulated this light quantum hypothesis, which basically says that light in existence and also in conversion processes or interactions with matter behaved as particles. And then there were famous experiments that tested this photoelectric effect, for example, by Philip Leonard and then also Millikan in 1916. Now, if we fast forward to today's quantum mechanics or quantum optics, we could say we know a lot more about experiments and from the theory side. One interesting insight is that there is a semi-classical limit of QED, quantum electrodynamics, that also works to capture some of the essential features of the photoelectric effect. However, what is interesting to note is that this semi-classical limit is a convenient approximation in the sense that it violates energy conservation. In fact, this was also noted by Einstein in the earlier days. So, for example, in a letter to Jacob Loeb, who was a dear friend of him, in 1910, he says that at present, I have high hopes of solving the radiation problem, and that without light quanta. I am enormously curious how it will work out. One must renounce the energy principle in its present form. However, 1 year later, in 1911, at the Solvay meeting, Einstein says that one can choose between the quantum structure of radiation and the negation of an absolute validity of the energy conservation law. Who would have the courage to make a decision of this kind? We will agree that the energy principle should be retained. So now, of course, in quantum optics, there are more experiments. For example, Bell inequality violation experiments. This is the only loophole-free test of non-classicality. And then there is experiments that have demonstrated sub-Poissonian statistics. This was and Hongou-Mandel effect. Sub-Poissonian statistics, for example, it was only demonstrated by Mantel, who was also in Rochester in the 80s. And then measurements of Wigner negativities and squeezing and other non-classical correlations of all kind. However, even then, it is very important to recall that observing matter and light exchanging quantum of energy, that is photons, in discrete units was an important first step in formulating the quantum theory of light. So in this work, what we ask is the following question: whether we can detect a graviton as exchange of energy in discrete units with matter and gravitational waves. Of course, this falls within the broader question of whether we can detect a graviton. And the conventional answer to this question is that it appears not feasible to detect a graviton. So among others, Dyson was one person who looked at whether LIGO, our best classical detector, can detect the strain amplitude corresponding to a single graviton. So one interesting observation is thing to know is that LIGO, a classical gravitational wave which LIGO can detect, if you estimate how many gravitons it corresponds to approximately 10 raised to 37 gravitons. That's a huge number. The way one would compute this is that we know the energy density of the gravitational waves in the LIGO band. We know that, so H0 here is the strain amplitude. It's just the amplitude of the wave, and we know that it's approximately in the LIGO band, it's between 10 raised to minus 21 to 10 raised to minus 23. And we can divide the energy density of this classical gravitational wave that LIGO is sensitive to with the energy density corresponding to a single graviton. So that is h bar omega divided by L cube, where L is the reduced wavelength for a single graviton. And this gives this number, which is 10 raised to 37. Dyson also looked into atomic processes and computed that the cross-section for observing gravitons is very small. However, Weinberg, for example, had this calculation also in his textbook. And the idea that, in optics or electromagnetism, the way we compute these spontaneous rates are the transitions in atom caused by electromagnetic radiation is to leading order dipolar in nature. But gravity couples to leading order through quadrupole moments. And because there is only one charge. And so one can compute, for example, what Weinberg does in his textbook is compute the transition quadrupole moment to estimate what is the rate that if a hydrogen atom, let's say, is initially in an excited state, spontaneously emits a graviton and goes to the ground state. So you sandwich the quadrupole operator between the excited state and the ground state and compute the dipole moment by performing the integral and use this to compute the rate. And what Weinberg found is that it would take approximately 10 raised to minus 44 or 10, the rate is 10 raised to minus 44 per second or hertz. In other words, it will take 10 raised to 44 seconds for the hydrogen atom to spontaneously emit a graviton and go to the ground state. Actually, later, Born and Rothman found that there was a slight numerical error in this calculation, and the rate that is actually is 5.7 into 10 raised to minus 40 per second. But if you compare this rate or the time that it would take, so it would take 10 raised to 40 seconds for a hydrogen atom to spontaneously emit a graviton. But then if you compare that to the age of the universe, if you compute the age of the universe in seconds, that is approximately 10 raised to 18 seconds. So what this means is that one has to wait much more than the age of the universe to see a graviton spontaneously emitted from the hydrogen atom. So needless to say, there is no chance of observing such a transition. And I would also want to quickly review how one would do such a calculation. So we are in this linearized gravity regime, where we study gravitational waves. So one could, so you know that general relativity has this huge local gauge degree of freedom. It is invariant under local coordinate transformations, and one can therefore fix apply all the gauge conditions to fix what are the physical degrees of freedom that are propagating. For example, slowly varying diffeomorphisms are a symmetry of the theory. So this allows one to reduce the 10 degrees of freedom to 2 degrees of freedom in this for a transverse and traceless wave that is propagating. So one identifies, just like in electromagnetism, there are two polarizations. These are the plus and cross polarization of the gravitational wave, and there's the amplitude. However, this transverse and traceless gauge is a very good representation to understand the physics of gravitational waves. But to see how they interact with matter or with detectors, it is better to go to another choice of coordinates, which is the proper detector frame or local in the local inertial frame. And there one can write down what is the interaction Hamiltonian to leading order. And one would find that the interaction Hamiltonian is quadrupole in nature. So the quadrupole moment of the detector couples to the gravitational wave. And there is, for example, this references here by Born and Rothman, for example, has a very good discussion about various gauge properties of this equation, this Hamiltonian, and appropriately taking the limits and so on. Also, Majori's textbook is a good example. So once we have the interaction Hamiltonian, then we note that we are in the linearized gravity, low energy regime of gravity. So whatever, of course, there are a lot of discussions about what is the correct quantum theory of gravity, but a global, more or less good consensus is that whatever the full quantum theory of gravity may be, in the linearized regime, it should be quantized as an effective field theory, as any other effective linear field theory. So this is done, for example, by Bronstein in 35, and so on. So what one would do is that in this approach, one takes the Fourier amplitudes from the solutions to a wave equation and then promotes them to operators. And then one can ask the question, what is the probability that the detector, in this case, the hydrogen atom, spontaneously emits a graviton and populates one excitation or one quanta in the gravitational field. And this computation then gives this number that Weinberg has computed. So one uses the density of states and so on in this calculation. So this is the standard Fermi-Golden rule calculation. So, and when computed for a hydrogen atom, it seems that hydrogen atom cannot be a good detector. But then our answer to this question is that indeed it seems it is possible to detect a graviton. And I would like to, before going into details of that, I would like to address what are the key differences to these previous approaches, for example. So the one interesting point is that Dyson was, for instance, looking at what is the sensitivity that LIGO would need to detect a single graviton. But one thing we know from the photoelectric effect is that to see single graviton exchange signatures, we don't need to have sensitivity at the level of a single graviton. So in the photoelectric effect, for example, we could have light shining on metal surfaces, which kicks out say, electrons. And then LIGO, after all, need not be the best detector to do this job, because to see quantized energy exchanges, one should measure a system, monitor the quantum jumps happening or energy jumps happening in a quantum system. And LIGO, which effectively measures position displacements, need not be the best detector to do this job. So we focus on, and then the other thing is that atoms seems to have very small cross sections to facilitate the detection process. So we focus on massive quantum systems, and then we consider stimulated processes in the LIGO band. It has two advantages. One, as I said, in LIGO band, we can classically confirm there was a wave using LIGO, that there is a wave that is incoming with as many gravitons. And then we combine with the quantum sensing of energy that allows to infer single graviton exchange events. So for this purpose, we use what are known as Weber bars, but with a quantum twist. So some of you may have heard the name Weber. Weber was a pioneer in gravitational wave astronomy. So around the time, I already mentioned that general relativity has this huge local invariance. So around the time when people were even debating whether gravitational waves truly exist or whether you could get rid of them by choosing an appropriate gauge, Weber was the person who told, let's take an aluminum bar and see whether we can see the aluminum bar ring up when a gravitational wave passes through. He had even made claims of detection, including, for example, I think in the 1987 a supernova event. But then there were not enough concurring evidence to say that it was valid detection. And then, of course, LIGO, which is a conceptually different way to detect classical gravitational waves, came along, and that became the more successful way to detect, which eventually led to the detection of classical gravitational waves in 2015. So in many regards, Weber's idea was to detect classical gravitational waves with these aluminum bars, but then they turned out to be a bad detector for classical gravitational waves. So what we do is that we take this property that it's a bad classical detector for classical gravitational waves and see whether it can give realistic regimes where it can be a good detector for single graviton exchange events. So for this, we also change the sensing method. So instead of measuring the position displacements, we measure the quantized energy levels of the Weber bar. So for this, we have to treat the Weber bar, which is essentially for all practical purposes, a huge block of aluminum quantum mechanically. So how do we do that? So one could think about think about a Weber bar as a lattice. So there are many atomic planes which are oscillating with respect to their mean positions. And then we can go to a collective coordinates. So instead of looking at these individual lattice planes, we can look at collective coordinates. These are acoustic modes of the cavity by applying elastic boundary conditions. And then one would see that you can also think about these lattice oscillations in terms of these collective coordinates. And these collective coordinates can also be addressed individually in experiments. So when you transform, and this what you see here is how you go from the individual atom basis to these collective acoustic mode coordinates. And it is for all practical purposes a change of basis, and we look into this system in a new basis. And then we can again evaluate what is the interaction for these acoustic modes, individual acoustic modes with the with the gravitational wave. And what one find is that there is a leading contribution. Both terms are quadrupole in nature. Note that there is a length factor that comes outside in the leading contribution. But the leading contribution increases with mass of the bar resonator that we have, as well as the length of the bar resonator. And this H double dot is the second time derivative of the gravitational wave. And then there is a subleading contribution, which is basically the added effect of Weinberg-like effect on individual atoms that form the Weber bar. But the leading contribution can be substantial in the sense that if you increase the mass of the bar as well as length of the bar, one can get a good collective response. So now we can focus on one of these collective modes and ask the question, what is the spontaneous emission rate? And we consider an niobium cylinder, and what one finds is that the spontaneous emission rate is 10 raised to minus 33 per second. So this is better than the Weinberg atom. Remember, it was 10 raised to minus 40 per second, but still much small. But then when we look at the stimulated emission or absorption rate, what one finds is that for a incident gravitational wave in the LIGO band, and if you consider aluminum cylinder, why do we consider aluminum? Because Weber was working with aluminum cylinders. One finds that there is the chance of seeing one graviton absorbed or emitted per second. Now, this is a very good rate for suggesting feasibility of detection. But I do also want to highlight that it is not surprising, because these Weber bars were indeed proposed to detect classical gravitational waves. And therefore, one does expect that there is some substantial possibility of feasibility of seeing a response in the detector. And that is when you translate that to a quantum mechanical treatment with monitoring energy levels, this is what it means. So you see a substantial possibility of detection with the Weber bar. And one could also solve the full time-dependent problem. So for this, one can look into the interaction picture and then use Magnus expansion or Lie algebra or such methods. And what one sees is that to leading order, the Weber bar gets excited to a coherent state. And in fact, one could consider one can also compute what are the parameters of describe the coherent state. So for a coherent state, the parameters are basically the amplitude and the phase of the coherent state. And we can, for example, write down the amplitude as a function of the incoming gravitational wave profile. So some of you may already have heard about this, that the gravitational waves that LIGO detects is not like a constant frequency monochromatic wave. So they are what are called chirping gravitational waves. So their frequency changes with time. But then there are some nice signals in the sense, for example, neutron star merger events, where this changing frequency over time will be very slow. So you can, over regions of the wave, you could, for example, treat it the frequency as almost constant. And then one can compute what is the probability that you see a single graviton absorbed from the, or you see a single quantum jump happen on the detector, and we get that it is approximately 36%. So that is the substantial, that is a maximum probability of the bar getting excited to the first excited state when it was initially in the ground state, stimulated by the incoming gravitational wave. And then we can also, for example, these chirping gravitational waves, there is a good understanding of the waveform and so on. And then we can, in this case, one could use to solve what is the amplitude of the coherent state. And we call this amplitude up to some prefactors chi. And one could write down, for example, for slowly varying signals such as neutron star mergers and so on. One could write it down in terms of the amplitude of the wave and then the chirp mass and of the binary source that is producing the signal. And another thing is that we can also use, now that we know what is the maximum probability of detection possible in principle, we can also use this to compute what should be the optimum mass for a single graviton exchange event in terms of this chirp mass and various other parameters. And yeah, another interesting thing is that this detector is a resonant detector. So what it means is that when a gravitational wave is chirping through, which means this frequency is changing slowly with respect to time, if the frequency of the incoming wave is much below the resonant frequency of the detector, we don't see much of a detection happening. And just when it is near resonance or at resonance, you see a sudden jump happening in the detector. So this is this characteristic of the sinc function, which is sine square x over x square that you see here. And then above the resonant frequency, you don't see much of an excitation happening. Another important thing to note here is that the probability of transition is proportional to the amplitude square. So what this means is that the amplitude square is basically proportional to the intensity of the incoming radiation or the number of gravitons that are there in the incoming radiation. So this means that at resonance or above resonance, once you increase the intensity, you see more excitations happening, or the chances of seeing an excitation or the probability increases. But this characteristic sinc function also means that it is like a step or a quantum jump like event that you would see in the detector. So now one needs so how do we see this quantum jumps happening in the bar detector? And this is where we need continuous quantum sensing of energy of the Weber bar. And this detection of energy is, of course, crucial because we want to see energy exchanges between matter and gravitational waves. And for this, we use this continuous quantum measurement model. And I want to give a very quick tutorial, one slide tutorial of what continuous weak measurements are. And of course, here we need to continuously monitor also because we don't know when a gravitational wave is going to be incident. So we essentially keep the detector operating for a long duration, reset it, and then keep operating and measuring, see if you catch a quantum jump. And the way it would work, what are these continuous weak measurements? So let's think about an analogous problem where for a 2-level system, a qubit or something, and where in the and an even simpler version where you want to see, you have a lot of butterflies in a nest, and these butterflies are leaving their nest and going towards 2 different trees. So in a conventional textbook strong measurement picture, you would only get to know which of the 2 trees the butterflies eventually landed. But with these continuous weak measurements, which is kind of state of the art that people are able to do in the experiments in superconducting and various other platforms, in addition to getting to know which of the 2 eigenstates of the measurement, or in this picture, the 2 trees the butterflies land, one can also track the evolution of the system or the route through which these butterflies here go from their nest to the tree, or the quantum system, how the quantum system evolves from the initial state towards one of these eigenstates of the measurement operator. And yeah, actually my PhD supervisor, Andrew Jordan, has a very nice book on this topic too. So here we simulate such possible, simulate a scenario where there is presumably we used a neutron star event. So what you see here on panel A of the figure is the continuous readout. And there is a blue line at 40 seconds, which means we reset the detector. And then we continuously look for events. And that pink window is a gravitational wave incident event simulated from LIGO data for about 4-second duration. And what you see here is that a quantum jump happens in that period. And which means that the occupation of the first excited state of our detector goes to 1, and from 0 to 1, and the other levels change accordingly. And in the right-hand side of this slide, we have a simulation where we also include some noise. Yeah. So this is how we would, so this is the scheme to detect these single graviton exchange events. The first thing to note that in our detector, the absorption happens at resonance. So this is a resonant effect, and this is very crucial for the inference of photons through photoelectric effect too. And then the probability increases with intensity. Only the number of such events, or the probability of that event, increases. That is evident from h square, or the intensity coming here. And then classical LIGO can tell whether there was a wave actually chirping through. So quantum jumps in materials can happen triggered by a lot of things. It could, for example, with these Weber bars, it could be due to seismic activities and other issues as well. But then we can increase the fidelity of the detection, because a classical LIGO, which is a classical detector for gravitational waves, such as LIGO, can tell whether there was a wave chirping through the resonant frequency of our detector at the time. And then we see single excitations happening in the bar. So similar to the photoelectric effect, we could call this a gravitophononic effect, because gravitons are converted into phonons in the bar detector. And then we note that the conservation of energy suggests that, which this kind of a semi-classical limit of QED or gravity would violate, which suggests that a quantum of energy or a graviton was exchanged between gravitational wave and matter. So essentially, when you see a jump happening when we see a jump happening in the bar detector, we ask the question, what does it mean for the wave? For energy, conservation of energy to hold, what this means is that the wave also lost one quantum of energy. However, this will not be a proof of quantum theory of gravity, but this would be a clue, a strong clue, or exchange of energy quanta analogous to the photoelectric indication for photons. So now we could see what are where are we at, and we look at different, for example, if we have a neutron star merger event, if we have a beryllium detector, which is approximately 15 kilogram, we see that there is high chance of, so these optimized mass and quantities are obtained from the calculations I just described. So if we have a beryllium detector operating with a quality factor of 10⁻⁻10, which is ground state cooled and maintained at 1 millikelvin, can see a single quantum jump happening in the bar detector due to the gravitational waves. And similarly, there are many other sources, and then we estimate what should be the mass that are needed for these events. And I should also mention that there are still some Weber bars or resonant, these are broadly called resonant mass detectors in still operation. And we can ask what is the upgrade that you need to see this single graviton exchange events. And the interesting thing is that we need approximately, so currently there are detectors in this plot. What you see on one axis is the characteristic strain. So this is effectively the strain. It is a language that people use in the gravitational wave community to denote what is compare different detectors and so on, for example. But and on the x-axis is the mass. So you see there are many stars and plus and cross and so on here, and they are either proposed or achieved characteristic strain or proposed upgrade for using different materials and so on. And what we broadly notice is that we need approximately 2 orders of magnitude improvement in terms of quality factors and cooling capabilities to reach the requirements of what we need to see single graviton exchange events. And compared to the technology we have, this 2 orders of magnitude improvement. So basically you need quality factors going from 10 raised to 8 to 10 raised to 10. And then one has to cool down from few Kelvin to millikelvin and also prepare the ground state of the system. So these are the kind of requirements we have, but there are still some Weber bars in operation. And one, of course, capability we do not have is this continuous sensing of energy at these mass scales. So I'll come to that briefly, which is of course but briefly summarize, we need single gravitons can be detected in principle. So previously it was thought that even considering such an experiment is infeasible, but we show that it can be done using macroscopic quantum resonators, and we would see stimulated single graviton absorption events. But this requires time continuous quantum sensing of quantum gems on the detector side or bar side, and then the weak interaction helps. So these bar detectors proposed by Weber were not good enough they were good, but they were not good enough to detect classical gravitational waves. But what we see here is that it gives reasonable parameter regimes where single graviton exchange events become the dominant effect, and it can be seen in principle in an experiment. But of course, this can be achieved with quote unquote realistic parameters. But what are the technical challenges? One needs quantum measurement at the macro level. As I was mentioning just a moment ago, this continuous quantum measurements have not been implemented at the mass scales like 15 kilogram that we are talking about. So one has to isolate acoustic modes of a 15 kilogram mass, which can be done. And then one has to continuously monitor the energy levels of this quantized object. And then we need to ground state cool Weber bars. So these are also, imagine ground state cooling a 15 kilogram object. And then, but it can also be done with various, so for example, LIGO mirror, which is something like 45 kilograms. They have cooled their motional ground state to very few phonons, maybe 9 or something in 2020 that time. And then one would also need to correlate with LIGO or other nodes, new sources, so that one can increase the fidelity of detection event. But I would say that this is again not a proof of quantum theory of gravity, but this is exchange of energy quanta analogous to the photoelectric indication for photons. And coming back to this earlier discussions about how our work relates to the early days of quantum mechanics, I would also want to highlight this essay that you can find on arXiv on stimulated absorption of single gravitons. This is more in the spirit of how people were in the earlier days figuring out that photon must be a quantum, and what this analysis mean for our proposed experiment. And finally, I would also want to highlight a recent paper that we posted on arXiv this week with Frank Wilczek on which is addressing a related question, which is whether how one can see this. What can you say more about this difference between semi-classical or coherent state description of radiation fields and departures from that? For example, what if the field is in a squeezed state or highly thermal state and so on. So this, if you are interested, you could also have a look at this reference. Finally, I would like to thank all my collaborators, Germain Tobar, Thomas Beitel, and of course Igor Pikovski, and all the various funding agencies and people who offer their insights. Thank you.
Thank you so much, Srinath. So if any of you have questions, please raise your hands.
Should I stop? I can stop sharing the screen.
Yeah, it's all right. I mean, people might
Okay.
want to read this. Okay. While people are thinking about the questions, I guess I'll
Yeah.
ask one. So I was wondering if it makes sense to ask. Yeah, sorry. Probably I'll hold my question because Arun Sebastian, can you please?
No, maybe you can continue with your question. I reserve my question later time. No problem.
It's all right. I'm the
Okay.
host. Yeah, I can
Yeah.
wait. Yeah.
Okay. Thank you. So if it's not kind of question, but if I understand correctly, this graviton detection is analogous to this photoelectric effect in which you stimulate your material or whatever the medium using the graviton, and you measure the stimulation, and you check whether this stimulation is comes from the graviton or, or it is in the regime of the graviton, right?
Yeah. So yeah. So
And
go on.
and this in the efficiency or the detection probability is proportional to this mass and length, right? And
Yeah.
can you is it possible to come up with some kind of, instead of using a single material, is it possible
Mhm.
to come up with a combination of materials like uh, like photonics or photonic chips is very
Yeah.
efficient to handling the photons and all these acoustic light
Yeah.
matter interactions, and somehow we can come up with a material combination like aluminum. I don't know if, whether it is possible or not, but some kind of combination is aluminum and these photonic materials inside it. So
Yeah.
is it possible
Yeah.
or?
That's a very good question. So one challenge, as you also pointed out, is that you need very good control of these acoustic modes, which are like collective oscillations of these atomic lattices, right? And it is not working with phonons is not a very easy problem. So you need, for example, some materials which have very good lattice structure, and then controllability, where you also these phonons, we also want these phonons to talk less with other possible sources of excitation, like other things in the medium. So engineering devices for this purpose is quite a good strategy. In fact, there is also other detector that we probably have in this list, which is superfluid helium. So it is one system that has been actually proposed by, I think Igor Pikovski also has a paper a few years ago for detecting classical gravitational waves, presumably, where the idea is that these systems have more control. You could have in principle more control on these acoustic modes and so on, that so that it is not like you are dealing with a bulk condensed matter system, but a system that is where you have more engineering skills, or all our engineering skills and control capabilities can be used. So that is indeed one possibility. And yeah, different materials where this can be done in better ways are definitely useful. What really matters for the detection point of view is whether it has the reduced mass that is relevant, and the quadrupole moment, which basically is a geometrical thing. So if you have mass distribution, it will have a relevant quadrupole moment.
Thank you. And one more question. Is it necessary to have the material, or in this case it is an aluminum rod? It is
Mhm.
necessary to have the straight aluminum rod or any curvature or any loop
Yeah, so actually current days, this I mentioned that there are some Weber bars already in operation. They are mostly going towards spherical detectors because you can then resolve, I mean, you can then uh, couple to gravitational waves coming in from any direction. So here we, in this simplified model, we assume a one-dimensionally so the gravitational wave is coming from top and it has this quadrupole moment in this uh, transverse direction, and that couples to the bar's quadrupole moment in that direction. So we assume a single polarization for the gravitational wave in these calculations, but it is quite easy and straightforward to generalize to spherical detectors, and this is what people who have resonant mass detectors, not all of them, but some groups are trying to do, to go towards spherical detectors for not their aims are very different. They use these spherical resonant mass detectors for various other purposes, detecting other things too. But yeah, this spheric shape can be changed. But of course, the nice thing is that you want to want a mass configuration that maximizes your quadrupole moment.
Okay, thank you. I would like to see. It's actually it's very interesting, and I would like to see the experimental setup because I know how difficult to deal with quantum
Yeah, thanks.
almost all fluctuation. And what about the temperature? Oh, you're cooling down it, right? Okay.
Yeah,
So
so one has to cool down to the ground state, and uh, we are hoping to see jumps from the ground state to the first excited state.
yeah, very nice work.
Thank
Yeah.
you.
Any further questions? Yeah, Manoj, please.
Hi. Thank you for the talk. This might be a naive question. So, in terms of number, what are we looking at? And if you are to build a detector of this kind,
Mhm.
what is the amount of materials required, etc., etc. If in terms of those numbers, what are we looking at?
Yeah.
Uh,
So, for example, if you choose beryllium as the material, and then you would need 15 kilogram beryllium uh, um, mass in one dimension. So it's like a cylinder which is 15 kilogram that could detect. But and these numbers of this type are not like for resonant mass detectors when they were originally conceived to detect classical gravitational waves, people have already achieved this mass. I mean, getting a mass of aluminum which is this much is, and this is not a challenge. The challenge is essentially where one has to ground state cool, and currently the temperature that we show we need is 1 millikelvin, and the quality factor. So the quality factor is basically omega. So it's the quality factor is related to the thermalization rate. So if I prepare the bar in the ground state, how long will it stay in the ground state? And there will be some time, and omega over that time is or omega, yeah, so omega over q tells this rate, or 1 over that time scale. So essentially we need very high quality factor basically to maintain our detector in the ground state. But we show here that we need 10 raised to 10, but 10 raised to 8 has been achieved, for example. So this plot here shows a ratio of Q over T for various things that have been achieved and where we want them to be. So it looks like we need a 2 orders of magnitude, and that is not too far-fetched. But of course, then there is also this problem of engineering quantum measurements of these individual acoustic modes at these scales, which is another interesting challenge.
Okay, just a follow-up question. You mentioned at the beginning that hydrogen atom would take a huge amount of time, probably longer than the age of the universe, to emit a graviton by
Spontaneous, yeah,
spontaneous emission. That is for
yeah,
a single hydrogen atom. But if you have huge amount of hydrogen atom, for example, like the neutrino detectors, they
yeah,
have water Cherenkov detectors. So we are
yeah,
looking in terms of multiples of Avogadro number. So
yeah,
when we increase that number, would that number be reduced, or what are
yeah.
the
So
what are your prospects? Yes.
Yeah. So there are two things with hydrogen atom. One is that, of course, when you look at collective numbers, so when you have more atoms and so on, then the 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 rates can be enhanced, and that is what we show in this work, because we treat this Weber bar as a collection of many atoms which are oscillating, right? But for the other question is what modes we are looking at, because hydrogen atom has these energy levels and there are frequencies involved there. Those are not in the LIGO band, and that is why we not look at a lot collective. So one could also engineer these collective modes of hydrogen atom that would give a similar enhanced effect. But then we also want to see those things in the LIGO band, because then there is the possibility of correlating with LIGO, which is a classical detector, which can also tell that there was a gravitational wave that caused the excitation that you see. So that can increase the fidelity of the detection. So it is true that collective effects can increase even for hydrogen atoms, and that is the physics will be is essentially what we show here as well. We look at collective atomic effects in this Weber bar that can give us the enhancement. And then we want to choose a system here, phonons, because then you can create those resonances which are like in the kilohertz range. So gravitational waves in the LIGO band are essentially somewhere between 100 to 300, 400 hertz. So this regime, or so you call kilohertz gravitational waves. And there you can create resonances, or you can create finite size for metallic systems where you have one has acoustic modes whose frequency matches the is also in the kilohertz. So that is the crucial thing here. Yeah.
Okay, thank you.
Yeah. Thanks.
Do anyone else have any questions? Yeah, Arun, please.
Yeah, so sorry, one more question. Like,
Sure.
so you have this aluminum rod, straight, let's say, straight
Mhm.
aluminum rod, and
Yeah.
this phonon vibration is happening. Like it start from the, is it start from the start of the rod, and it oscillate towards the end and back and forth. It's like a,
Yeah, no. So this is quadrupole oscillation, right? So it is defined with respect to the center of mass of the rod. So it starts basically from it's something like about the center of the road, and then these are oscillations about it. So the first fundamental mode, it is like a sine function about. So if you remember this, it's a lot like this open pipe, closed pipe kind of problems that we do in undergraduate, and then they have this fundamental
okay.
modes, right? So there these oscillation, and those are also acoustic because you sound waves inside these things. So yeah,
Okay,
it's a bit
so
like that. Yeah.
okay. What was I thinking? Like, if you instead of having straight rod, if you have a closed loop kind of things,
Uh-huh.
this oscillation goes forever. I mean, this is now it's become n times whatever the quantity. So
Yeah,
because
yeah.
you have n loops, so
Uh-huh.
these n loops again enhance your detection efficiency within the same length and with the same mass.
Yeah,
So
so even closed, yeah, exactly. So quadrupole moments also, there is this x square minus y square kind of term, and then xy cross term. So if you
yeah,
look,
some kind of
yeah,
elliptical shape, right?
exactly, exactly. So these are so this is what one would want to match to, because the gravitational wave is causing those. So when you say the gravitational wave has plus and cross polarization, what it means is that it is creating a circular distribution of masses to move in that way or this way. So you probably have seen in this gravitational wave polarization talks that they show a distribution of circular masses which oscillates this way or that way to show the plus and cross polarization. So so when you have a system that does that, you want a detector which can also do that. So that is essentially the idea. So a simpler model is just one dimensional, but more like if you want all directions, that's where one would, for example, take a spherical detector that would take care of all possible directions of incoming radiation too.
Yeah, thank you.
Yeah, I guess this is the point where I can ask the question.
Yes.
This is probably very naive. So I was wondering if there is, like some material where, like if it gets phononically excited, then there is some other electric excite, I mean, like a piezoelectric material or
Yeah.
something where, there is an indirect signal.
Yeah.
Does that make sense to?
Yeah, actually, I should have yeah, I don't think I have the reference, but this what you're saying is the possibility of transducing this signal to another element which can be detected. And yeah, so Igor also has a recent paper with Germain where they look at this possibility. So the idea is that you could have one can transduce these oscillations which or the ringing up of the bar in the larger mass to possibly to a smaller element through transduction, where so essentially this can be done in principle too. So this can in principle reduce the requirement of having to do the detection at a larger mass, but yeah, this needs to also there will be associated challenges that one has to account for them. But this transduction is, I should say, there are also experiments at lower masses, like not kilogram, but milligram and so on, where transducing the excitation from acoustic to some other mode is an interesting problem on its own. Yeah.
Interesting. Thanks.
Yeah.
Yeah, if I may, there is one more question.
Yeah, please.
So I was wondering if, it makes sense to look at something like a mesoscopic effects, like, I mean, not a single graviton excitation, but a few gravitons, let's say 10,
Yeah.
hundreds, or a few tens. I mean, does it make sense to look for such effect, that is mesoscopic quantum effects of gravitational field?
Yeah. So I think,
And
yeah, okay, that's a very good question, because it's so you're not you're saying not in the 1, but not in the 10 raised to 37, but somewhere in between, right? Yeah. So there are two things. One, if you go from beyond one click detector, so this work that I mentioned briefly with Frank. So we asked the question. So this is broadly applies to any radiation field. So you have a radiation field that is interacting with the resonant detector, whether there can you see distinctions from a coherent state of a field. And what we show in this work is essentially one of the key results is that one could compare the probabilities of seeing 0, 1, 2, like the lowest order detection probabilities, to come up with a measure whether the detector, the radiation field is in a coherent state, so that one could take the semi-classical limit or not, or what if it's in a squeezed state or so on. And what we find is that, including for this graviton detection problem that we just discussed, it is realistic that one could monitor this 2 or 3 jumping to the third excited state or second excited state, these events to discriminate, for example, for a highly squeezed vacuum state. In this context, I should also mention that Frank has previous articles called The Noise of Gravitons. And the work there is that if you look at the geodesic deviation equation for 2 test masses, so this is almost like the LIGO setup. One will do, if the gravitational wave incident on the 2 test masses is in a quantum state, such as a squeezed vacuum state, this will incur a correction, a noise term into the geodesic deviation equation. And this noise can be very significant for if the gravitational wave is in a highly squeezed vacuum state, for example. So such signatures can already be measured. So what we show in this work is that it can also be done with resonant mass detectors. So there is that possibility of going just above one detection event. But then if you go to the mesoscopic scale, which is, you could talk about a little bit more, more number of excitations and so on. So the same statistical treatment applies. So you could do, essentially the idea is that one could do quantum statistics, but then I think this, beyond that, where this is still regime where one has control, but then in the strictly mesoscopic, like you have finitely many gravitons, I think it's a very interesting problem to consider.
Great, thanks.
Yeah.
Okay, another related
Yeah.
question is about the, something called, this memory effect that's been discussed in the context of gravity and electromagnetism. So this corresponds to cases where the perturbation doesn't just vanish in the future infinity, but rather it settles to some constant value. For instance. So what that means would be that, when let's say a detector is placed in such a field, it would, since it's saturating to a constant value, I think it'll excite the system to something like like if you assume the field to be exactly classical even, then the detector will saturate to a coherent state. Like even because essentially what I'm trying to say is that do you think such effects can be measured, the memory effect?
In principle, yes. So the memory effect is that you have a distribution of masses initially, and the wave passes through, and then there is a change in the distribution of masses that is not going to zero in the long time limit, I guess, something like this. Yeah, and it's an interesting question, and in principle, yes, I think, but I also had this question from another another person I know. So yeah, there is I think potentially yes. So these detectors can in principle probe such memory effects too. And the question is what is the difference? Like what are the, like how strong is the memory effect, and what are the chances of actually seeing it? And yeah, that one needs to be looked at more carefully, I would say.
Yeah, thanks. I mean, the other reason I asked the question is that the quantum version of this memory effect is that they are related to asymptotic symmetries of the quantum theory of gravitation. So it's so fundamental to the quantum theory of gravity. So yeah, it would be interesting to have like some kind of a experimental perspective on
exactly.
From that side.
Yeah, that's very interesting. Thanks.
Okay, so if there are no other questions, let's thank Sreenath again for a nice talk. Okay, so yeah, that concludes the session today. Thank you so much for attending.
Yeah, and thanks for organizing to all of you. Thank you very much.
Bye.